Hey, Kristen, how's it tracking?
With Carvana Value Tracker?
What else?
Oh, it's tracking. In fact, Value Surge Alert trucks up 2.5%. Vans down 1.7.
Just as predicted.
Mm-hmm.
So, we gonna...
I don't know. Could sell, could hold.
The power to always know our car's worth.
Exhilarating, isn't it?
Tracking.
Always know your car's worth with Carvana Value Tracker.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Echoes from the Cosmic Dawn, The Hidden Life of Red Galaxies and Perseveranc uncovers Martian history. Echoes from the Cosmic Dawn. Mapping the early universe has long been a central pursuit in cosmology, aiming to unravel the mysteries of the universe's infancy. The period known as the Dark Ages, occurring after the emission of the cosmic microwave background, CMB, and before the formation of the first stars, remains one of the least understood epochs. This era holds crucial information about the formation of the first structures in the universe and the nature of dark matter and dark energy. However, observing this period is exceptionally challenging due to the faintness of the signals and interference from Earth's atmosphere and human-made radio frequencies. To overcome these obstacles, scientists are turning their attention to the Moon, specifically its far side, as an ideal location for radio astronomy. The Moon's far side is shielded from Earth's radio frequency interference, providing a pristine environment for detecting the faint signals from the early universe. Several projects are underway to deploy lunar orbiting satellites equipped with radio antennas to map these ancient signals. One such initiative is the collaboration between the British company Blue Sky Space and the Italian Space Agency. They are designing a fleet of CubeSats intended to orbit the Moon and detect faint radio signals from the universe's early periods. These satellites aim to capture signals from the Dark Ages before the formation of the first stars, offering insights into the universe's infancy. The project builds on previous efforts, such as NASA's Rolls 1 and the upcoming Lucy Night project. Blue Skies also proposes integrating their satellites into ESA's Moonlight program, which envisions a constellation of satellites for lunar communication and navigation, thereby enabling accurate positioning and data transmission for the observation satellites. Similarly, China's Hongmeng project, also known as the Discovering Sky at the Longest Wavelengths (DSL) project, plans to launch an array of satellites into lunar orbit to observe the sky at ultra-long wavelengths. This mission aims to probe the early history of the universe by detecting signals in the 0.1 to 30 MHz frequency range, which are inaccessible from Earth due to the ionosphere and radio frequency interference. The project envisions a mother satellite and several daughter satellites forming a linear array, with the daughter satellites conducting observations and transmitting data to the mother satellite for processing in communication with Earth. These lunar-based observations focus on detecting the hydrogen 21 cm line, a spectral line emitted by neutral hydrogen atoms. This line serves as a powerful probe of the early universe, providing information about the distribution and state of matter during the Dark Ages. By measuring the 21 cm signal, scientists can gain insights into the formation of the first stars and galaxies, the nature of dark matter, and the processes that led to the reionization of the universe. The deployment of lunar orbiting satellites for mapping the early universe represents a significant advancement in our ability to study the cosmos. By utilizing the Moon's unique environment, these missions aim to overcome the limitations of Earth-based observations and open a new window into the universe's formative epochs. The data collected from these missions will not only enhance our understanding of the universe's origins but also inform models of cosmic evolution and the fundamental physics governing the cosmos. The Hidden Life of Red Galaxies. The universe doesn't come with an instruction manual, but if it did, Charles Steinhardt, assistant professor at the University of Missouri, suspects there would be entire sections missing. Either the cosmos has always been governed by rules we don't fully understand, or we've misread the script from the start. For decades, astronomers have comfortably placed galaxies into two broad categories: blue ones, teeming with young stars and actively forming new ones, and red ones, characterized as older, quieter systems that have ceased star production. This classification, long considered foundational, is now being reconsidered. Steinhardt proposes that there is a third, overlooked type of galaxy, one that complicates the binary and challenges how we interpret cosmic history. These are red star-forming galaxies. Unlike the blue galaxies bursting with high-mass, luminous stars, red star-forming galaxies give birth to mostly low-mass stars. Their appearance remains red, not because they're old and inert, but because the kinds of stars they form don't shine as brightly or as blue as their massive counterparts. According to Steinhardt, this distinction isn't just cosmetic, it solves a couple of deep, unresolved problems in astrophysics. One of them concerns the long-standing discrepancies between black hole mass and stellar mass. Another issue lies in the differing initial mass functions observed in blue and red galaxies, distributions that determine the variety of stars formed at birth. These differences couldn't be adequately explained by aging or by the usual suspects like galactic mergers. What Steinhardt and his team are proposing is more than a new label, it's a revised narrative of the cosmos itself. If red star-forming galaxies were more prevalent or influential than previously understood, our estimates of total star formation across the universe's history might be far too low. In other words, the universe might be significantly more productive than we've assumed. The consequences of this are broad. It would alter the way astronomers interpret the timeline of galaxy evolution, forcing a revision of models that once followed a clear, linear path from youthful blue spirals to dormant red ellipticals. This idea spills over into how we think about other odd types of galaxies as well, such as post-starburst galaxies. These have traditionally been explained as the aftermath of violent mergers, where two galaxies collide, leading to a quick burst of star formation that exhausts available gas and leaves the system in a quiet, red state. But what if that's not always the case? Steinhardt proposes that some post-starburst galaxies may never have gone through such an intense phase. Instead, they might have slowly and steadily produced low-mass stars, enough to classify them as still-forming stars, just not in the way astronomers have been trained to look for. If this is true, the very definition of what counts as a post-starburst galaxy may need rethinking. Some of these systems may be quietly thriving in their own red-hued way. The implications are enormous. If this third category exists in meaningful numbers, it opens the door to a new interpretation of how galaxies live and die. It challenges long-held beliefs about stellar populations and the mechanics of galactic evolution. It reframes what we thought we understood about the color and life cycle of the cosmos itself. Steinhardt isn't working alone in this endeavor. At the University of Missouri's Department of Physics, undergraduate students are already preparing to expand the investigation. Matthias Harper and his team will delve deeper into the evidence, trying to identify more galaxies that might fit the red star-forming profile. Simultaneously, Carter Meyerhoff and Zach Barawiak are leading a separate effort using data from the European Space Agency's Gaia satellite, which tracks the positions and properties of over 2 billion stars within the Milky Way. By analyzing this vast trove of data, the team hopes to shed new light on stellar populations and the kinds of stars that dominate different galactic environments. If these efforts bear fruit, it could mark a turning point. The story of galaxies may no longer be a simple two-act play with blue beginnings and red endings. There may be a whole middle chapter, written in shades of red, waiting to be fully understood. Perseverance uncovers Martian history. NASA's Perseverance rover has been exploring the rim of Jezero crater, uncovering a remarkable variety of rocks that provide a unique window into the geological history of Mars. This area has turned out to be a treasure trove of intriguing rocky outcrops, offering valuable insights into the planet's past and its potential to support life. Since January 2025, Perseverance has made significant progress in its mission, with the rover extracting core samples from 5 different rocks along the crater's rim. These samples are then sealed in tubes for future analysis and returned to Earth. The rover has also conducted in-depth investigations on numerous other rocks, employing tools like a laser to study 83 additional rocks from a distance. This marks the fastest pace of scientific data collection since the rover landed on Mars more than 4 years ago. The rover's climb up the western side of Jezero crater took about 3.5 months, with Perseverance reaching the rim on December 12, 2024. The science team now finds itself exploring a 445-foot-tall slope, known as Witch Hazel Hill, where they have been discovering a stunning diversity of rocks. This abundance of varied geological features was more than the scientists had hoped for. In earlier missions, finding unique rocks for study could take months, but here on the rim of Jezero, new and fascinating rocks are found everywhere. The area around Jezero crater's western rim is particularly interesting because it contains rocks that were once deep underground, ejected by meteor impacts that occurred billions of years ago. These rocks, many of which have been fragmented by violent impacts, sit next to well-preserved layered rocks that formed at the surface in Mars' early geologic past. Some of these rocks show signs of past water activity, while others have remained relatively untouched by water over the eons. The variety and age of these rocks allows scientists to trace the planet's geological evolution over a vast timespan. One of the earliest rock samples taken from this area was named Silver Mountain, which Perseverance collected on January 28, 2025. This sample came from a rock known as Shallow Bay, believed to have formed at least 3.9 billion years ago during Mars' Noachian period, which marks the planet's earliest geologic era. The rock may have been altered by an ancient meteor impact, which is common in this region. Another intriguing discovery was made a short distance away, where a different outcrop contained igneous minerals that crystallized from magma deep within the Martian crust. These minerals are particularly valuable because they preserve information about the conditions that existed when the rock formed. However, not all attempts to sample these rocks were successful. Perseverance tried to core a rock containing igneous minerals, but 2 attempts failed due to the rock's crumbly texture. The rover then moved to another site, 520 feet away, where it successfully collected a sample from a rock called Tablelands. This rock is composed largely of serpentine minerals, which form when water interacts with iron and magnesium-rich rocks, a process that often causes the rocks to expand and fracture. The serpentinization process can also produce hydrogen gas, which may play a role in the creation of methane in the presence of carbon dioxide. On Earth, such rocks are known to support microbial life, making them particularly intriguing in the search for signs of past or present life on Mars. One of the challenges Perseverance faced in collecting the Tablelands sample was sealing the sample tube. The powdered rock at the top of the tube made it difficult to achieve a proper seal. To solve this problem, the rover's team employed a technique known as a flick maneuver. This technique involved using the rover's robotic arm to vibrate the tube, clearing any obstruction at the top. After several attempts, the team was able to successfully seal the sample on March 2, 2025, ensuring that it could be stored for later return to Earth. After sealing the Tablelands sample, Perseverance collected another sample from a rock called Main River, which was notable for its alternating bands of bright and dark minerals. These bands were unlike anything the science team had seen before, suggesting that the rock had undergone a unique geological history. The rover has continued to explore Witch Hazel Hill, analyzing additional rocky outcrops, such as Sally's Cove, Dennis Pond, and Mount Pearl. The team is eager to continue their investigations, confident that more exciting discoveries await. The exploration of Jezero crater's rim has proven to be a whirlwind of scientific activity, with each new rock sample providing valuable data that will help researchers piece together the story of Mars' past. Perseverance's mission continues, with the science team using the data they have gathered to plan their next steps in this exciting chapter of Martian exploration. As they continue to study the crater rim, they remain hopeful that more groundbreaking discoveries are just around the corner.